here. So let's have a look at the idea behind solutions by power series, and we will review some aspects from culture related to power series. Okay, so suppose we have this equation y prime equals to y. Okay, and well, when it comes to setting a solution in the form of a power series, that is y equals to sigma n equals 0 to infinity c sub n x to the n. And if we expand the series, well, for n equals to 0, that's c sub 0, x to the 0, which is invisible 1, c1 x to the first, c2 x squared, c3 x cubed, c to the 4, etc. But in this case, we also needed the derivative of this series. Well, that'll be, well, since the dummy variable here, well, it's x, just use the general power rule, n times c sub n x to the n minus 1. Well, essentially, take the derivative of this polynomial here, you know? I mean, the derivative of a constant is 0, and then C1, the derivative of C1x is just C1. The derivative of C2x squared, that's 2C2x to the first power. I mean, a bunch of general power rules. You guys following me here? What's going on here? All we're doing is just differentiating a polynomial. Okay, so I'm going to substitute this into the differential equation. Well, so that is the derivative of the series, which is this one right here, C1 plus 2C2x plus 3C3x squared plus 4C4 x cubed plus 5C5 x to the fourth plus dot 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 equals to y, the origin series without differentiating. That is C0 plus C1x plus C2 x squared plus C3 x cubed plus C4 x to the fourth plus C5 x to the fifth plus dot dot dot. So we have a problem here, guys. I mean, unfortunately, we can't write all these infinitely many terms, you know? I mean, this is the only one time I'm going to take this approach into solving this equation because it works for this easiest example. And guys, remember undetermined coefficients? Well, essentially, that's what we're going to do. So check. The constant equals the constant. That means C1 equals to C0. And then what else? With a different color, 2 times, well, the coefficient of x to the first power on the left equals the coefficient of x to the first power on the right-hand side of the equations. All right? That means 2c2 equals to c1, which means c2 equals to 1 half c1. But needs to express C1 in terms of C0. Isn't it true from the previous part that C1 equals to C0? So this also means C2 equals to 1 half C0. Okay? So far, so good, you guys. Following me here. We're just equating coefficients and writing everything in terms of C0. Okay, what's next? Let me do another one. Let me do another equating of a coefficient. How about the coefficient of x squared equals to the coefficient of x squared? Okay, so okay, let me set it up. So 3c3 equals to c2, which implies c3 equals 1/3 c2. But what is c2? Isn't that from before? 1 half C0. So what we're going to get is coefficients that depend on the previous one somehow. Okay, so this will be equal to C3. Okay, wait. This implies C3 equals 1/3 whatever C2 is, which is 1 half C naught. All right. Let me just do one more. Actually, we don't have to do that many, but let me just do one more. Okay, with a different color. Okay, we use red. Hmm. Yeah, do this brown instead. Okay, brown. Okay, so the coefficient of x cubed equals the coefficient of x cubed. Okay, that is one more here. 4c4 equals to, what is that? C3, which implies that C4 equals 1/4 C3, which at the same time writing C3 in terms of C1, what's C3? So C4 equals to 1/4 times 1/3 times 1/2 C1. And this is good enough, guys, to see a pattern of numbers. Do you see what happens every time we write a new coefficient? Can you identify the pattern? What is it? What do you notice about it? The factorial, right? So that means, okay, boom, boom, boom. If I keep going, C5 would be uh, 1/5 times 1/4. This is time, not minus. 5 times 1/3 times 1/2. Well, I guess 1/1, but we don't need to write that 1/1, right? C naught, which is the same as saying C naught over n factorial. Okay? And we're essentially done. In general, wait, not yet, not yet, not yet. This. In general, what we're trying to say, C sub n will be uh, n, n minus 1. Or actually, let me do the product the reverse way so you guys don't freak out about it. So, how about 2 times 3 times 4 times 5 times dot 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 times n, all right? Times C naught. This is essentially 1 over n factorial C sub n, C naught, all right? So now we have the coefficient C sub n that we exposed in our solution, you know? So let's see, let me use this color. So C sub n, which is all this, I'm going to replace this guy over here. All right, that's what we're looking, the coefficient of the variable x. Okay, so the general solution, y equals sigma n equals 0 to infinity c sub n x to the n, which is sigma n equals 0 to infinity of c naught over n factorial x to the n. This is the series solution, guys. This is, let me take the constant outside, n equals 0 to infinity x to the n over n factorial. This is our series solution. Okay. Did you recognize that series by any chance? Huh? That's the exponential function, okay? So y equals c naught e to the x, but in this case, we would go just like y equals c e to the x. You may wonder, why to do all this mess of finding coefficients using series while this equation, y prime equals y, can be solved by separation of variables, isn't it? This is a very nice and simple separable equation. dy over y equals dx. Integrate both sides. That's actually going to give us ln of x equals x plus c. Exponentiating both sides. Wait, ln of y. Y equals c e to the x. Same, isn't it? Well, for this exercise, everything works just nice and easy. All right. So if you look at this example, you're like, well, it doesn't seem as bad as it looks, right? I wish that were true because I mean, this is the idea behind, right? We have, or well, we may have a bunch of potential issues here. A lot of take into considerations, rather observations here. Okay, that's on the next page. Observation number one. Assuming a solution of the form y equals sigma n equals 0 to infinity of c sub n x to the n does not always work. Okay, so that's number one. I'm going to show you some cases in which it will not work. Okay, later on. Number two, we need to take into account the convergence of the series. And for these guys, let me give you an example. Consider the series, okay, where C7 is just an invisible one, okay? Let's talk about the series sigma n equals infinity of x to the n. Isn't that the geometric series for with common ratio equals to r? Okay, well, simply expand 1 plus x squared plus x cubed, etc., and so on and so forth. Okay, what about for x equals to 0? Okay, so the value for y equals to, what is that? 1 plus 0 squared plus 0 cubed plus infinitely many zeros. In this case, the value of the sum converges to 1, right? What about for x equals to 1? Are we going to be that lucky? Okay, so y equals to 1 plus, 1 plus 1 squared plus 1 cubed plus 1 to the fourth plus infinitely many ones. Does that sum converge? This diverges. This blows up to infinity, right? So diverges. For x equals to 1/2. What about it? Okay, well, let's do the substitution. So that is y equals to 1 plus 1/2 squared plus 1/2, plus 1/2 first, plus 1/2 squared plus 1/2 cubed plus dot dot dot, you know? But isn't that the same? Okay, this is actually the same as saying 1 plus a half plus 1 1/4, if you will, plus 1 over, what is that? 8 plus dot dot dot. Okay. Do you recognize the series, the kind of series? What is it? Well, we already said it's geometric, right? Well, actually, what do we know about sigma n equals 0 to infinity, x to the n? Isn't that the same as saying 1 minus x, provided x, the absolute value of x is less than 1? That's actually the radius of convergence of the geometric series, right? So that means if we choose a value between -1 and 1, except the endpoints -1 and 1, and actually we just saw that it diverges for the endpoint 1. Every value in between, excluding the endpoints, will have our series to converge. And if it converges, we can find the infinite sum using this formula here. Infinite sum equals 1 over 1 minus a half, which is 1 over 1/2, which equals to 2. So the infinite sum equals to 2. Okay? There's a joke. Have you heard? Have you heard about the joke? So there's a mathematician walking into a bar. He orders a beer. And then another mathematician walks into the bar, orders half a beer. A third mathematician walks into the bar, orders a quarter of beer. The bartender just figures it out and he serves 2 beers. Right? So, well, what else besides the convergence of the series? Well, oh, again, when it comes to convergence, to checking the convergence of a power series, we have three cases, if you remember from calculus 2. Okay, so number one, case number one, a series only may converge only at its center. Zero in the case that I just showed you here. However, in general, okay, in general, sigma n equals 0 to infinity of c sub n, x minus x naught to the n, where in this case, converges for, no, converges at its center, which is simply x equals to x naught. You might remember you do the ratio test and then take the limit, and if you end up with a 0, the radius is infinity. If you end up with an infinity, the radius is 0, and if you end up with a number, you end up with an inequality that you need to test the endpoints to keep checking the convergence of the power series, especially these endpoints. So that's case number one, the case in which a series just converges at its center x naught or a. Maybe in calculus you saw it as a, but it's the same. It's the same thing. It's the same thing. Case number two, the series converges for all values of x in the real numbers like the exponential function converges for all x. Sine and cosine, their power series representations converge to for all real numbers except for some functions. We're going to get there eventually. So that's case number two. Case number three converges within negative r and r, where r is the radius of convergence. However, also in general, if we have a power series n equals 0 to infinity, c sub n, where the series is not centered at the origin, so just a little bit of terminology. A series centered at zero, that was called Maclaurin series, while a series centered at at a value other, at a center other than zero, that's a Taylor series. Just a little bit of vocabulary, you know? So converges for absolute value of x minus x bar, I mean x naught, less than whatever radius is, which is x minus x naught smaller than r and greater than negative r. And then you keep solving the inequality and then test the endpoint. I'm going to show you an example soon. Okay. That being said, after considering, the previous idea of the convergence, if we can express the solution as a series y equals to sigma n equals 0 to infinity, c sub n x to the n, then it is guaranteed that the derivative exists and can be calculated in the following way. I mean, just take y prime, just like we did before with the derivative of the series. Y prime equals to sigma n equals 0 to infinity of n c sub n x to the n minus 1. Now, here is the thing. One of these main aspects from calculus 2, when you were checking the interval of convergence for a power series, so in this case, it may, oh, actually, this should have been just a greater than, not greater than or equal. Okay. So actually, this may change for the derivative. Maybe these endpoints become both including the endpoints. Maybe one becomes inclusive and the other one exclusive, maybe, or maybe like this, or maybe the radius of the interval of convergence remains the same. That's going to depend on the type of series we get. I'm going to show you an example of this. All right. So as a note, and converges. Oh, yeah, I have it here. Converges in the same interval as the original series, except possibly at its endpoints. That's where we may have some changes. I'll show you. All right. Well, now here's the thing. For this power series, later on, I would be increasing the index every time we take the derivative, because what happens? So when you're differentiating the first term, which is a constant, c sub 0 is going to go to 0. So now your first term is going to be having the coefficient C1. So the proper way, in a way, to start the index here is at n equals to 1. But that's something I'm going to discuss a bit later today. Okay. Observation number 4. The expression for C sub n, it's not going to be always easy to obtain like the one we just did with x to the n over n factorial. It's not always going to be easy, if possible to do, you know. And number 5, which is a consequence, if you will, of number 4, if for some reason you still manage to get the sigma notation for the series, maybe it's not easy to relate it to one of the elementary functions like we did in this case to the exponential function. Okay, so you'll see how is this math is going to work. Okay. Find the interval of convergence of the series sigma n equals 1 to infinity of x to x minus 1 to the n divided by n. Okay, this is basically calculus 2 review. Okay, so what do? we're going to do the ratio test for this one. I mean, if you, I'm just going to go an example. I'm going to go, I mean, I'm going to cover this briefly. However, if you're interested in more details, you want to review, there's a calc to playlist in my YouTube channel. All right. So, in case you want to see a little more, okay, a sub n over n, a sub n plus 1 over a sub n, that equals the limit as n approaches infinity of, what do? Shift every index by n by 1, that is x minus 1 to the n plus 1, divided by n plus 1. Everything divided by x minus 1 to the n over n. That is the original rule. And we take the absolute value because we end up having some alternating series. We need to think about those. Okay, dividing by a fraction is the same as multiplying by the reciprocal. So that is the limit as n approaches infinity of. Uh, okay, I'm going to write this x minus 1 to the n plus 1 as x minus 1 to the n times x minus 1 divided by, all I'm doing is loss of exponents, everything divided by n, and I'm going to multiply by the reciprocal of this, which is n over x minus 1 to the n. Okay, and I mean, I'm doing this so I can simplify this quickly. Okay, also cancel the ends and see what you check what we get. We get limit. Uh, wait, we get no. Hold on. What am I doing? N plus one here. Okay, n plus one. All right. So yeah, that's the only thing we get to factor. Okay. So n. Okay, actually, much better. When we're computing the limit, the dummy variable in this case is n. So this x minus 1, I'm going to take it out as absolute value of x minus 1 because again, we don't have any idea of what the value of x is. So we better keep this absolute value. That is times the limit as n approaches infinity of n over n plus 1. What is that limit equal to? Equals to 1. So we get the absolute value of x minus 1 times 1, which is absolute value of x minus 1. But what about that? Again, by the ratio test, that quantity we just got converges for setting it less than 1, diverges if we set it greater than 1, and it's inconclusive for equal to 1, but we want to check the convergence, so that's why we're going to set it less than 1. Okay, so from here, what do we do? Okay, so from here, this means x minus 1 less than 1 and greater than negative 1. Solve inequality, add 1 to both sides. That is 0 less than x less than 2. Okay? And guys, this right here is the potential interval of convergence. Why do I call this the potential interval of convergence? Because the second half of this problem is to go back to the original series and test these endpoints, x equals to 0 and x equals to 2. If we're going to get a series of numbers, no longer variables, to check their convergence. If the new series we come up with converges, well, then that inequality becomes that I mean that less than becomes an equal also. But if we end up with a divergent series, well, that remains the same. So that's what we need to check here. Okay, so how about it? For n equals to 0, what do? Write a whole new series. Okay, substitute x equals to 0 in the original power series, sigma n equals 0. Oh, wait, 1 to infinity. We would have problems with 0 here, right? So that is 0 minus 1 to the n over n. Isn't that sigma n equals 1 to infinity of negative 1 to the n times 1 over n, right? Here is where we need to keep in mind the 10 different tests for convergence and divergence of series from Calc 2. We can see this is an alternating series, so how about the alternating series test? For the alternating series test, we need to, so by alternating series test, AST for short, letter A, we need to take the limit of a sub n as n approaches infinity. Here, a sub n without the alternating factor, that is just the 1 over n, all right? That is limit n approaches infinity of 1 over n. And this limit equals to 0. And well, one of the conditions, one of the initial conditions for the alternating series test is that this limit equals to 0, all right? So letter B, we need to make sure that this sequence right here is decreasing. A sub n plus 1 less than or equal a sub n. That is this statement true? 1 over n plus 1 less than 1 over n. Is this true? So yes, clearly the denominator on the left-hand side is larger and giving us a smaller number on the left-hand side of the inequality, making that statement true. What does that mean? Converges. Okay, that means converges. Okay, number 2. For actually it's not for m, it's for x equals to 2. Okay, let me change this for x equals to 2. All right? So, that is sigma n equals 1 to infinity of 2 minus 1 to the n over n, which is 1 over n, 1 to the n, right? Sigma n equals 1 to infinity of 1 to the n over n. But 1 to the n is just 1. You guys agree with that? I mean, doesn't do anything. N equals 1 to infinity, 1 over n. What do you think about that series? Diverges, converges, diverges by which series? Well, it's a harmonic. It's this particular harmonic. However, diverges, or simply call it divergent, P series. Divergent P series, all right? Okay. So now that we have all this, let's see. Hmm. Let's write the actual interval. Yes, we're still going to have the following between 0 and 2, okay? However, because for the lower endpoint of x equals to 0, we end up with a convergent series that less than becomes less than or equal. Because for the upper limit of x equals to 2, we got a divergent. Well, we don't include that that endpoint. So this is just, oh, I'm less than only, right? Okay, guys, let's take the derivative of this series. That is, consider let y equals to the same series n equals 1 to infinity of x minus 1 to the n over n. All right? Find the derivative y prime. That is sigma n equals 1 to infinity. That's n times x minus 1 to the n minus 1. You guys agree with this? Divided by n. Okay. See how the n's are going to get canceled? And at the same time, check. This is the same as saying sigma, okay, n equals 1 to infinity, x minus 1 to the negative 1 times x minus 1 to the n. This series may look crazy, but actually this is just a geometric series, right? Because, okay, check this out. This will be equal to sigma n equals 1 to infinity 1 over x minus 1 times x minus 1 to the n. Isn't that just a? Isn't that just r? That's a geometric series, right? So guys, to for a geometric series, there is no need, okay? There is no need to do this ratio test because, well, look at the summary. I'm giving you a summary of our series from below. Here for the geometric series, the interval of convergence is whatever ratio, or u in this case, between -1 and 1, okay? That is uh, x minus 1 less than, I mean, greater than -1 and less than 1. That means x less than 2 and greater than 0. Now, do you see the difference of the interval of convergence, or I mean, compared to the interval of convergence of the original series versus its derivative? It contains the exact same number still, the exact same endpoints, all right? Except that what may change is the inclusion or exclusion of such end, all right? So, and I mean, for more details, if you want to see more exercises about this, there's a call to on my playlist on my YouTube channel. Just have a look at it. Okay, I'm still going to do a brief review of representation of function here. That is e to the g, the exponential function, sigma u to the n, sigma n equals 0 to infinity, u to the n over n factorial. Typically, you would see this series with x's rather than u's, but I changed the variable from an x to a u because what if you have a composite function? So that u would be more representative of a more generalized function that includes some sort of a composition here. All right. So this is a formula sheet for power series representations on the functions. There's a couple more for the sinh u. Okay, it's the same minus the alternating factor, and for the cosh, that's also the same as the cosine, but without the alternating factor. I might give you those more formally later on an assignment or something. Okay. Another calc to type of exercise. Express the function f of x equals x cubed e to the 5x as a power series centered at 0. I mean, we don't need to do anything. So when we're given a function composed like this, okay, you want to focus on the elementary function. What do I mean by that? The exponential, the sine. I mean, notice the x cubed. Ignore the x cubed. Also, the exponential has an exponent other than just x. So that means we have a composition function. So this is what I would like to do. F of x equals to x cubed times e to the u, where in this case u equals to 5x. All right. Similarly to what we did with the first translation theorem in the previous chapter. All right. So this means x cubed sigma n equals 0 to infinity um, u to the n over n factorial, where u equals to 5x, and then simply go back, substitute x cubed sigma n equals 0 to infinity of 5x to the n over n factorial. And I'm going to do a couple of things in one shot. Number one, I'm going to introduce this x cubed into the series and multiply with the power of x, which is x to the n. This would be number one. Well, let me actually do one more step. X cubed sigma n equals 0 to infinity. That's 5 to the n, x to the n over n factorial. Now I'm going to multiply the x's together. Sigma n equals 0 to infinity of, what is this? 5 to the n, x to the n plus 3 over n factorial. And that is the power series representation for this function. When we get to solve the differential equations with this series, we're going to do the reverse actually. You'll see it soon. Okay? So, so one of the other are very important aspects we need about power series. It's shifting the indices here. All right. Well, um, how to shift an index? It's gonna be one of the primary tools to get to the solution to the differential equation. Well, so actually, I'm going to discuss two different shiftings. Okay, a complete shifting and an incomplete shifting. So, for instance, oftentimes we may need to have a series that has a starting index at a very particular number. And in some cases, we may need to add or subtract a number in order to achieve that starting index. So, for instance, I mean, in summary, whenever, whenever we add if we add a number to the starting index, we need to go the reverse for every instance of n in the general rule inside the period. That is, if we add a number inside of in the starting index, we subtract as many units to the ends inside. And vice versa, if we subtract some number, do the reverse, add those number of units, the same number amount of units to the series inside. This is what constitutes a complete shifting. Okay. Now, what about incomplete shifting, which is another kind of shifting that we may need when it comes to solving differential equations using power series? In some cases, it's possible to simply change the starting index from 0 to 1 or backwards without having to change anything in the rule because check this series. Sigma n equals 0 to infinity and c sub n x to the n. So what would you get if you substituted n equals to 0 to get the n equals 0 term? That would be 0, c sub 0, x to the 0. I mean, do you guys agree that you're going to get a 0? That term is going to disappear. So what would be the first term that you will see in the series? The term with n equals to 1. So that's why you can change back and forth the starting index to 0 and 1 or vice versa without doing the complete shifting because check this out. Because if I expand this series, for instance, that's 0 c sub 0 x to the 0 plus 1 c sub 1 x to the first plus 2 c sub 2 x squared plus etc. What is that going to be equal to? 0 plus c1 x plus 2c2 x plus etc. Right? Plus c2 x squared, right? So what's the first term that appears? Isn't that C sub 1? Now have a look at the series below. The series sigma n equals 0 to infinity of n times n minus 1 c sub n x to the n. That's exactly the same as simply changing the starting index to 1 or change the starting index to 2. That's not going to affect anything. And the reason to that is because if I expand this one, okay, that's 0 times 0 minus 1, c sub n, I mean c sub 0, x to the 0, plus 1 times 1 minus 1, c sub 1, x to the first, plus what's the next one? 2 times 2 minus 1, x c sub 2, x squared, plus 3 times 3 minus 1, c sub 3 x cubed plus dot dot dot. Do you guys agree with what happens to the first two terms? They go to 0 because they produce coefficients of 0, right? So this goes to 0, that goes to 0. So what's really legitimately the first term of the series? Isn't that the one that starts with the index 2? So this is the reason why we can change back and forth between one and the other one. Okay? So what is this? So 2 times 1 is that 2 c2 x squared plus 3 times 2 is that 6 c3 x cubed plus. I mean, all I want to show you is where do we start really. So guys, the real trick when it comes to solving differential equations with power series is to Be skilled with combining these two techniques plus something else, okay? But we're gonna get there soon, okay? We're getting there, all right? We're just having a look at some tools that we need, some prep that we need to get to solve a natural differential. Okay, as examples here, shift each of the series so that the starting index starts at n equals to n equals to 0. Okay, so the starting index here is n equals to 2. So if we wanted to turn that n equals to 2 into an n equals to 0, we would need to subtract 2 units, right? However, if we subtract 2 units starting index, we would need to add 2 units to every instance of n that you see inside of the series. All right? So here we go. That is then sigma n equals 0 to infinity n plus 2 c sub n plus 2 x to the what is 2 minus 1 is that n plus 1? Okay? So this would be the new series after shifting the index with having a starting index at n equals 0. Number letter B. We have a series that starts at n equals to 1. Okay? So subtract 1, okay, to make it a 0. However, if we subtract 1, let's actually add 1 to everywhere else. So plus 1, and plus 1. All right? So this will become sigma n equals 0 to infinity of n plus 2 c sub n 1 minus 1. This is just going to be c sub n, all right? And x to the n plus 1. Final answer. Shifting indices. In some other cases, we may have other needs, like maybe not having a series at a particular starting in. No, maybe this time we care about the power of x. So let's say we want to write this series, this given series, so that the terms involve an x to the n power. Okay, focus on the x to the power, on the x to the power. So check. To turn this x to the n minus 1 into an x to the n, we would need to add 1 unit, isn't it? But in this case, we need to do a complete shifting. So add 1, but then you have to shift all the n's inside the series. Add 1, add 1. Now, what do we do with the starting index? Subtract 1, all right? So this would be sigma n equals 0 to infinity n plus 1 c sub n plus 1 x to the n. Final answer. Okay. What about letter B? What do we do with the power x to the n plus 2? Subtract 2, but we don't just subtract 2 to the x to the n minus 2. We need to subtract to every instance of n in the general rule and do the opposite in the starting index. Okay, so subtract 2, subtract 2. We do add 2 here. Okay. Okay. So sigma n equals 2 to infinity of n minus 1 c sub n plus 1 x to the n. Final answer. All right. Okay, guys, one more tool and we're getting there. One more tool, adding and subtracting power series. Okay. So in order to combine two or even more power series into a single one, all series must have the same starting index n and the same power of x. It's like combining like terms, combining so like series have the same starting index, the same power of it, or the power of x. Now, what's the general strategy that we're going to follow here? So the general strategy will be we would look to write all series in terms of the highest power of x that you see. In some cases, we may do some other trick, some other processes, but in general, this is the trick of the trade here. Okay, what are we going to do? A combination of complete shiftings, incomplete shiftings, or both. And in some cases, we may need to expand some of the terms of the series. You'll see, let me show you this example right here. Okay. So, example number 5, and we call it for the section. Sigma equals 2 to infinity of n times n minus 1 c sub n x to the n minus 2 minus sigma equals 0 to infinity of c sub n x to the n minus 1. Actually, there's a few strategies to go about this one. I'm not gonna lie, but let me follow the one I have in my notes because it's a combination of pretty much everything here. So here's the thing. Which one is the highest power of x? N plus 1, isn't it? The one in the second series. All right. The lowest power is n minus 2. Now, here is the thing. Also, if we compare the starting indices, we have a 2, we have a 0. But the question here is, how many units are these exponents apart from each other? 3 units, right? So 3 units apart. Now, so the minute you see these guys, what would you do? Naturally, what you would do is add 3 units, blah blah, right? That's what you may think of doing. But we have a big problem, guys, here. Yes, we need to do the opposite, which is subtract 3 on the starting index. We have a big problem with that. The problem is that the starting index would be a negative number, outputting a potential negative exponent. The definition of a power series is that contains only positive integers and zero. For negative exponents, that's something else. That's Laurent series, which you'll get to see in complex analysis. Not now. That's something else. All right. Okay. So, guys, what would you do then? So here is where making a wish come true comes into play. All right. So didn't we wish, okay, did we wish the starting index were a 3 here? So I can subtract the 3 and get the starting index of 0 and finally combine the two series together. Well, let's make the wish come true. How about expand n equals to 2. Okay. Because, okay, so that'll be 2 times 2 minus 1, c sub 2, x to the 2 minus 2, plus, what would be the next term? Wouldn't that n equals to 3, and then n equals to 4, and then n equals to 5, and so on and so forth? You guys agree with this? Okay, so, but I'm not going to write the polynomial. I'm just going to start writing the series sigma n equals to 3 to infinity n times n minus 1 c sub n x to the n minus 2 minus the other series n equals 0 to infinity. What is that? C sub n x to the n minus n plus 1. Okay. And now we should be able to do the trick. All right. Okay, so what is this? 2 c sub 2 x to the 0, which is just, okay, let me write the x to the 0. Okay. So now let's do a complete shifting. So minus 3 plus 3 plus 3 plus 3 and plus 3. This way, not only we get the starting index at n equals to 0, we also get the power of x to have both of them to be n plus 1. All right? Okay, so this would be plus. Hey, what's going on here? Okay, there we go. So plus sigma n equals 0 to infinity of n plus 3. And what is that? Plus 2. Okay. C sub n plus 3 minus sigma n equals 0 to infinity of c sub n x to the n plus 1. Now that we finally have, yes, the x of n, yeah, right? Yeah, x to the n plus 1 minus, okay? Now, thank you. Now we have two like series. They have the same starting index, the same power of x. So 2c2 x to the 0 equals to 1. We don't need to write that 1. Sigma bracket n plus 3, n plus 2, c sub n plus 3 minus c sub n x to the n plus 1. And starting at 0 to infinity. Essentially, I'm factoring the sigma symbol on the left and I'm factoring the x to the n plus 1 on the right. Okay? And everything containing the c with the subscript and the n plus 3, n plus 2, etc., that remains inside. Final answer. And I believe this is it, right, for the section